Hey guys, super quick introduction. I just want to say I put so much effort into making this video. I think it's the best one out there for NLP sentiment analysis in Python. If and when you do like the video, please drop a like on the video and consider subscribing to the channel, and I'll see you in there. Today we'll be using the Twitter sentiment analysis hatred dataset available at this Kaggle link. You can see there's train and test.csv. We actually only need train, and we're going to download that and upload that into our environment over here. If it got uploaded as a .zip file, you're going to want to unzip that with unzip train.csv.zip, and you should see now a .csv file. We can now read this as a pandas data frame, import pandas as pd, train.df is pd.read.csv in the name, output train.df. We should see our data frame here, where we have the index column, our ID, which is simply one number up from the index, the label, which is 0 if it is not hatred, 1 if it is hatred, and the corresponding tweet. We'll try to make a machine learning model or a sentiment analysis model that, given a tweet, it can try and figure out if that is a label 0, meaning it's not hate, or label 1, that it is hate. We can check the distribution of the different classes. Train.df sublabel.value counts, 29,720 of the rows are 0. Most of them are not hatred, 2,242 that are hatred. This is called an imbalanced dataset, as there's much more of one class than there is the other. Do a wget, which simply downloads the file glove.6b from Stanford. All these things are GloVe embedding vectors, which is a fancy term for converting a word to a set of numbers. We'll choose, say, 50 numbers to convert each of the words to. Once that's finished downloading, you should see glove.6b.zip, and we can unzip that, and we'll see that it made 4 different files. We're simply going to use the 50d one, meaning each of the vectors are 50 dimensional. We're now going to create a function that can take this file and turn it into a dictionary mapping the words to vectors. So import numpy as np. To start out with just this blank dictionary called words, then we're going to make this function define add to dict d and file name, where we'll pass this words dictionary in there, and file name we're just going to be passing this file. So we're going to open the file, so with open, then file name r, and we'll open that as f. Then we'll read all of the lines of the file. So for line in f.read lines, iterating through each of the lines of the file, we get line equal to line.split on space. Because if you go to look at the file, you'll see everything in the line is separated by spaces. I'm first just going to print line. We'll get rid of this after, and I'm just going to break. We will call this function. We will pass in this thing words over here. File name we're going to pass is this file right here. And we can see this is the first line of the file, where it has some word. This is the word the, and then it has several different things here. There's actually going to be 50 different numbers all in strings. Also, there's this \n over here. So these numbers form the vector for this word. We want to grab all of the words or all of the lines and make a dictionary from the word to its corresponding vector. Now, in case there's any problems with the file, it's a good idea to write the word try. Do d sub line sub 0. Add to the dictionary, d is our dictionary, this key. This key is line sub 0. This is line sub 0. We'll make it the numpy array of line from 1 onward, so that this is the corresponding vector that we're plugging into that word. So we'll try to do that, but if some sort of error comes up, except we'll go into this block instead, and we're just going to continue. We're just going to move on to the next line. We can call this function we made with simply add to dict words. That's our blank dictionary. We'll build up words, passing the name of the file. We can see that our output of words, it's this dictionary of words mapping to their corresponding vector. So question, is this 50 dimensional vector? We could check how many words we have in this dictionary with simply the length of words, 400,000 different words. We'll use the very popular NLTK library for some natural language processing tasks, nltk.download wordnet. Now we need to do what's called tokenize, so we'll make a tokenizer equal to this thing, regular expression tokenizer. It's easiest to see what this does with an example, so it has this action called tokenize. So we do tokenizer.tokenize and then some string. This is actually the first tweet in our training data frame at user when a father is dysfunctional and is. We can see that that parses or tokenizes into the list of user. It got rid of the at, and then when a father is dysfunctional and is. It's much easier to parse different tokens this way rather than the full tweet. It's much easier to use this rather than its original string form. Now we need to do something called lemmatization. From nltk.stem import wordnet lemmatizer and make a lemmatizer equal to that thing. Basically, this is just an object that can lemmatize, similar to tokenizer.tokenize. It'll lemmatizer.lemmatize a word, and that will take user and then convert it to its lemma. For example, converting user to its actual lemma, lemmatizer.lemmatize user, we can see that its lemma is also user. That one stayed the same, but if we instead had the word say feet, its lemma is actually foot. It converts words to more common representations. I'm now going to copy and explain our function that takes a message like this and does all the processing to convert it into a token list. Just like this, but a little bit more processing. Message to token list, a string s. So given a message as a string, it converts it to a list of tokens. It gets that original list of tokens with tokenizer.tokenize the string. Then it is a list, so we'll do lowercase tokens, t.lower for t in tokens. That just lowercases every word in the sentence. Then we do lemmatized tokens with just as above, we do lemmatizer.lemmatize t for t in those lowercase tokens. And then useful tokens is t for t in lemmatized tokens if t in words. We only keep those tokens if those words are actually in this list here. And as you can see, all of these are lowercase. Now, of course, we actually have to return this, so return useful tokens. If we call this with message to token list, pass it, for example, first string in the data frame, user when a father is dysfunctional and is. You can actually see that that's really the exact same thing here. If we had a different sentence, feet fathers, so multiple fathers, well, that converts fathers to its lemma father, and feet, that converts that to foot. That is our processing function for each of the tweets. Now, the reason we got the word embeddings is so that we can replace user with its word embedding, and this with its vector and with its vector and so on. We want it as a list of vectors representing those words. We'll make this function and call it message to word vectors, so it takes the raw message just like this and converts it to its ordered list of word vectors. It does that using the word dictionary, which we called words. Processed list of tokens, aka this result, is equal to message to token list, passing that the message. Now that we have that as a list of tokens, we're going to build up one by one this list of vectors. It starts with nothing. We do for token in the processed list of tokens, and we say if the token is not in the word dict, so that's our word embedding dictionary. If we actually don't have a vector for that, well, just continue and move on. But if we do, that means we can get token vector is equal to word dict sub token. That just says whatever word that we saw there, grab its corresponding vector, vectors append with that token vector. At the end, we should have every vector in a list, and we can return as a numpy array, numpy.array of vectors, making sure that the type is float. If we took that same string as before and we called message to word vectors on that, see that we have its corresponding list of vectors right here. That's a little bit tough, so we do dot shape. It is 8 by 50, meaning that we have 8 different tokens, 1, 2, 3, 4, 5, 6, 7, 8. They all got converted to actual vectors, and those are of course 50 dimensional. It's now important to convert our data frame or our training data frame into train, validation, and test sets. We train the model on the training set, we evaluate its performance immediately on the validation set, and we leave to the end as a final model evaluation on the test set. The code for this is a little bit boring, so I'm simply going to paste it in. I am saying that the first 70% of the rows go to the training data frame, the next 15%, so from 70 to 85, they go to the validation data frame, last 15% is test, so it's 70 train, 15 validation, 15 test. We have 22,373 rows to train, 4,794 to validation, 4,795 to test. They are stored in train df, val df, and test df. Just so you can see all the code if you're interested, scrolling over to the right for a second. Make a function df to xy, where x is our inputs and y is our corresponding outputs, given either the train data frame, validation data frame, or the test data frame. Getting y is pretty easy. These are our observed outputs, a data frame, which I'm calling dff, sub label. We'll convert that to a numpy array, and we'll make sure that it's an array of integers. Now this code is the trickiest part, but stick with me here. We're going to build up this thing called all word vector sequences. This is our inputs, empty list at first. For message in the data frame with sub tweet. So this goes through and gets each of the messages. Message as vector sequence. We had a function to do that with message to word vectors, message to word vectors of the message. If message as vector sequence, so this object, if its shape sub 0 is equal to 0. Why am I checking this? What that means is if this component here is 0, that means that we had no usable tokens in the tweet. It turns out that this does actually come up. If that is equal to 0, I will instead set that equal numpy.zeros with a shape equal to 1 by 50. This is something we'll fix later. All word vector sequences, so this thing that we were trying to build up, dot append with the thing that we just grabbed, message as a vector sequence. Now something we want to do, but currently can't, is convert this into a numpy array. We cannot do that because different messages will have a different sequence length. We will have a different number of tokens tokens in each message. So for now, we simply return all word vector sequences as well as y. So we'll use the train data frame, calling df to xy on train df, x train, and y train is what it'll produce. We do print length of x train itself. We see it has 22,373. Looking at the length of the first message, well, the length of that first message, 13. If we instead look at the second message, well, that length is 8. This next one, 7. This is varying in number. It can't be a NumPy array because that value is changing. We actually need to perform some simple data analysis on these sequence lengths. So we'll do sequence lengths, empty list for now, for I in the range of the length of x train. And if we do sequence lengths dot append with the length of x train at I, import matplotlib.pyplot as plt. I indented that wrong. And then if we do a histogram, plt.hist of sequence lengths, you can see here that the majority is between 0 and 35, and there's maybe one that's a little out here. A very useful pandas function, we first have to convert it to a series, so pd.series of the sequence lengths, and then we do .describe. Most interestingly to us, the maximum is 55, meaning that we don't see any single message that has over 55 useful tokens. To make it a proper NumPy array above, we really need each of the sequence lengths to be exactly the same. We don't want this to be 13 and that to be 7. Let's just make them all the maximum. So if the maximum is 55, well, actually I'll choose 57 just to be a little bit more safe, but we're going to make all of the messages now a length of 57. But naturally they don't, and so what we're going to do is something called zero padding. Pad it with zeros until it gets to 57. So I'd say I lied earlier. This is actually the most complicated piece. From copy, import deep copy. This simply is a utility function to make full copy of an array. Define pad x. It just takes, x train, x val, x test, whichever one you want to get, x, and desired sequence length, and we'll set that equal to 57 by default. We'll start out with just making a copy of the array. So x copy is equal to a full deep copy of x. Then we use Python's enumerate function. So we do for I and x in enumerate x. Each the index, so this will go 0, 1, 2, 3, and so on. And this grabs the actual element in the list. Now, if we're iterating through this capital X thing, each X, this is actually a NumPy array. What this really is a sequence of vectors. Remember that. Sequence length, so what it currently is, we're going to change it soon, that's equal to x.shape sub 0. However many vectors we currently have, that is that number there. Then we can get the difference between the desired sequence length, so 57, sequence length difference is equal to the difference, so 57 right here, minus its current. Okay, so this is a value that better be positive because this value is the maximum out of everything. This is a value that says how many zero vectors do we need to pad to make it equal to 57. Now, what are we actually going to pad? Well, we're going to call that, we'll call it pad is equal to numpy.zeros. So we're only going to give it zeros with a shape equal to, well, the sequence length difference, because that's how many vectors that we need. And this better be 50 because that is the dimension of all of the vectors. We don't want to change that. Now that we have that, we can just do x copy at I, so overwrite what it previously was and set that sequence of vectors equal to the numpy.concatenate x, so that's what it previously was, and then pad. So we're just padding at the end with zeros. Note that first x comes and then we pad it with zeros after that. Now we can actually make this a NumPy array. So at the end of all of this, we can simply return the numpy.array of x copy. Let's just make sure that those are floats. Now let's test this out with x train. We can pad this with x train is equal to pad x, and passing it x train will keep the desired sequence length as 57 and see that x train actually has a shape now, and its shape is 22,373. So that's how many tweets we have. Each of those are 57 by 50, meaning that they are sequences of 57 vectors. If it didn't actually have 57 tokens, well, then we padded it with zeros, and all of those vectors better be 50 dimensional. ytrain.shape, and it gives the corresponding outputs for each of these inputs, 373, matching right there. We can prepare our validation and test very similarly with xval and yval is equal to df2 xy, that function previously, sending that val data frame, and then set xval equal to, we have to pad that as well, so xval, and we can look at its shapes and see that it has 4,794 tweets with the same dimensions and the outputs matching up. And the code is very, very similar for test, just one more observation for the test. Now we did the tricky part. We just need to define the model and train it, which is really easy. We're going to do from TensorFlow.Keras import layers, and then from TensorFlow.Keras.models import sequential. We'll make a sequential LSTM based model. We can start our model from scratch, simply being model is a sequential, and we'll make the first layer in that model by model.add an input the shape of 57 by 50. Remember, we don't specify the number of things we're sending it, just the shape of those things, which are all, we have 57 vectors, and those vectors are 50 dimensional. We'll now add a relatively arbitrary number of LSTMs. Do model.add a layers.lstm or GRU, they're pretty much the same thing. LSTM is just more complicated. Make that 64. This could be any number. 64 is usually a good starting point. We'll do return sequences equal true so that we can actually stack this LSTM. To add a little bit of dropout. This is just for regularizing or shrinking the coefficients of the model to avoid overfitting. Then what we can do is just kind of copy this piece a couple of times. We'll get both of these, and well, since its return sequence is equal to true, well, LSTMs take sequences, and so we can actually replace that with an LSTM, and we'll give it the dropout as well. Maybe one more for fun. I don't even know. It doesn't matter what you do. Try and play around with what you want. Now, if we define that model and just output its summary for now, we'll see, of course, that it's not quite what we want, but taking a look at it, it ends in 57 by 64. Well, first, we actually have to really flatten this thing. You could probably do some sort of an averaging technique as well. Layers.flatten, and then end it in a sigmoid, dense 1 activation sigmoid. Make this note the probability that whatever input we gave it, the probability that it is a hatred message. We'll see the whole thing except the input. I don't know why it never shows the input, but it outputs in just one node, which is what we want. Because this is what we call a binary classification task, the loss that we're going to use is called the binary cross entropy. From TensorFlow.Keras.losses, we'll import binary cross entropy, use an optimizer, which I pretty much always use Atom. From TensorFlow.Keras.optimizers, import Atom. TensorFlow.Keras.metrics, import AUC. And so that we can save only the best model, we are going to do a checkpoint. So we'll do from TensorFlow.Keras.callbacks, import model checkpoint. CP for checkpoint, the model checkpoint, instantiate that. We'll pass the model directory, so we're just going to save it in a file or a folder called model, save best only equal to true, so that when it's training or going through the epochs, it's only going to save to this directory the best model. We now have to do what's called compile the model. So model.compile, set the optimizer equal to an atom. I set the learning rate equal to 0.0001. You could maybe try 0.001. Loss equals binary cross entropy, and metrics we'll look at, just give it the string of accuracy. Since it is a imbalanced dataset problem, we have much more of the one class than we do the other. We'll look at something also like AUC, look at some better ones afterwards. Now, as I just mentioned, this is an imbalanced dataset problem. We have many more non-hate messages than hate messages. So we have to do a little extra step here to incorporate that, to weight the loss function more, so give more attention to the hatred messages because there's less of them. Value counts of train df label, we saw that above. We do frequencies, 21,000 and 1,500 of the other one. Now, I don't want to explain the code for this. You can look at the math if you want to, but we can get the weights like this. For this class, the non-hate messages, I'm going to weight you just 1.07. But for these ones, well, I'm going to weight that about 14 times more than the other one. If you multiply this by 14, you'll get approximately this number over here. We can now finally call model.fit. To train it, we pass it xtrain and ytrain, our inputs and our observations. Then we get the validation data, which is xval and yval. We set it to say 20 epochs should be enough. Callbacks, we need to make sure that we call that checkpoint we created and set the class weights equal to those weights as above. Before calling this, make sure that you are using some sort of a GPU, or make sure that your laptop or computer is using a GPU. Now, I just lost everything because what I did is went to change runtime type and GPU, and so you'll have to actually rerun the code. It may or may not, it most likely did, get rid of the file that you uploaded here for the train.csv. So apparently co-op dislikes me right now and it's training a lot slower than it used to. We have a val AUC of 0.9, which I'm already pretty happy with. I'm just going to stop this from TensorFlow.Keras.models. models, I will import their load model function, and then we'll get best model is equal to load model, and we store that in just model slash. Now I can get the predictions for the test set, so test predictions best model dot predict with we got x test before greater than 0.5. Only make the values true if they are bigger than 0.5. We will make this dot as type an integer, so they are all either zeros or ones. We'll make a final evaluation of our model with from sklearn dot metrics. We'll import the classification report. By the way, if you are actually trying to get the best model, you shouldn't be looking at the test set quite yet. You should be tweaking things in the model over here and then trying to get the best accuracy or AUC or whatever on the validation set, and then only do this at the very end. Print the classification report with, we need to pass that the actual truth, and that is stored in yTest, and then our predictions are test predictions. Now for this particular model, we didn't get a phenomenal average. A macro average on the F1 of 0.65 is not amazing, it's okay. If I actually let the model train how it was supposed to and not cut it off early, it would have gotten maybe 0.73, 0.74, which is a little bit better. And if you actually spent the time to tune things, you could probably get it past 0.8. But that isn't really the point. If you appreciate this video, please drop a like. If you aren't subscribed already, got lots of tutorials and content for machine learning, so please subscribe as well. And I'll see you next time, guys.